You've got another great one titled How to Constrain Artificial Stupidity. And I found out prior to recording that these are two of your personally favorite talks.
Yeah, yeah,
Um,
I'm pretty happy with those talks. Yeah,
we'll we'll include links to those in the show notes. Do you want to fill us in a bit on this constraints topic? Um,
sure.
yeah,
So, the one thing that helps to mention here is that I skipped around in college, and my no, so like so there's a couple of reasons why. Like, let's say that you have a very good algorithm. It has 99% accuracy on whatever task. Like, one awkward thing that might happen, right, is that people start trusting it blindly. And that's not necessarily the algorithm's fault, but you do have to kind of wonder, well, um, maybe the world changes, but if no one is checking on that, this whole blind faith in algorithms thing is definitely something to watch out for. But there's also like subtle things that can still go wrong. So, for example, let's say I have a very highly accurate model that does classification, and let's imagine, um, we have a 2D plot where in the middle there's green dots, red dots, and blue dots. Let's say. And the algorithm is very good at separating the blue dots from the red ones from the green ones. If you go to the scikit-learn landing page, you see you might have seen this image. And let's say that we really have a good accuracy on this. Well, then something you might want to do is you might want to say, well, hang on, maybe the model can be uncertain sometimes. So what I want to do then is when the model's uncertain, which is usually like the near the boundary region of these 2 points of two colors, maybe we want to say, oh, let's not automate a decision there because we are uncertain. That's something you might want to do. Okay, and we have a very highly accurate model. So then when it's uncertain, it's probably also going to do something good for us there then, right? That's good. But here's the awkward thing. If we think about the red dots, right? Um, you got to imagine that there's like a region where we are certain. And if you think about how these algorithms sometimes work, there's usually like a binary line that separates the red dots from the rest. And on one side, it's basically saying it's not red. And on the other side, it's saying the further away on that side you are, the more red it gets.
mhm.
So now I can say, okay, let's imagine that we have a new data point coming in that's miles away from any data we've seen before, but it's definitely in that red region according to the boundary line. Well, then it's unlike anything you've seen before. So any algorithm that says I'm super certain it's red will be wrong.
Right,
This is,
right, right,
I
right.
apologize a little bit because this is way easier to explain with like a visual.
Yeah, visuals. But I guess like the general idea is that a model that is very accurate on your training data, when you have out of sample data points in reality, it can act extremely confidently about those out of sample data points.
But the same argument you can have for your validation data set too. As long as whatever comes in production is different than whatever you trained and benchmarked on, right?
Mhm, mhm,
Accuracy is not enough, even on a test set.
mhm, mhm.
And there's also like and there's lots of these experiments that you can do. And my blog has a couple of these benchmarks where on your training and validation set, a random forest is better, but then you increase the noise on your data, and then maybe a logistic regression is better. It kind of depends on your definition of the problem. But the main thing I really like to drive home is just this idea that when you report an accuracy number, it is just a number, which is a huge reduction of what happens in reality. And it
Mhm,
comes from this academic background where if you have a data set, you want to run a benchmark, you need a number to compare.
mhm.
But always remember that CSV file you have on disk is not the same as reality. And then reducing that down to like a single number we optimize for is
Mhm,
skipping a whole lot of aspects of your problem, maybe. So
mhm.
like, feel free to take some of those numbers with a grain of salt. You can run a very mature benchmark, but it's hard, and you want to think about it a couple of times before you pick an algorithm based on a number you ran
For
somewhere.
sure. You need to be investigating individual cases, and thinking about what's going on here, like what's happening in situations where your algorithm is most confident or least confident, or when it most confidently misclassifies something. What's happening in these situations can be extremely interesting because if you just follow, there are all kinds of in my years deploying models into production. There are countless scenarios where if I had gone by accuracy or area under the curve metrics alone, I would have deployed disastrous models in real life because they were doing funky things.
It's stuff like, "Hey, I've built a chatbot, and the performance on my data is very well." huh? Why is someone talking French to it? I've only benchmarked it on English.
Mhm.
There's all these axes of problems that go well beyond an accuracy number. Um, I might write a book at some point called "Accuracy is Not Enough." That's like the main thing I want to communicate here, because there's so many things that can still go wrong, even when the accuracy seems amazing.